I don't know what the catch is.
Maybe you can
So, shall we start then? It's good. So, hello everyone. Thanks for having me here. And I'm Amir. I used to be a PhD student at the Biomedia Imperial College London, and now I work as a research assistant there. And I'm having my Viva next month, so good luck. I will be talking about a project that I have been involved recently. Is related to training artificial intelligence for medical imaging tasks. I will start with the media, what they are talking about medical imaging. There's a hype. If you know Jeff Hinton, the godfather of deep learning, he said something like they should stop training radiologists now, and during 5 years AI will replace radiologists. Of course, this didn't entertain everyone, didn't like it, especially from the clinical side. And then there's a guy which is named Curtis Langlot. He's professor from Stanford, and he's from the clinical side, and he said, answering the question, will AI ever replace radiologists? He said, I say the answer is no, but radiologists who use AI will replace the radiologists who don't, which actually makes more sense than the first answer. And this is usually the answer from people who work in this domain and people who work from outside. So the AI hype is big, and it worked really well on natural data or natural images, and you have seen it in Google and Facebook and other companies, but while in imaging, it's more challenging. So the hope, we have some companies now work in health data in general, including imaging. You have the AI giants like DeepMind, Microsoft, and Amazon. Recently, they also acquiring reports, and they try to mine the data from the reports using AI. And there's also imaging-based companies, startups like Babylon. They do skin detection, and also they have a phone app for interviewing with GPs. There's also for the cardiac imaging, like heart flow, they can detect some disease using the images, using also AI methods. And the list is long. So there is something happening now. The market is expected, there was a research on Signify, and they expect the market cap will reach 2 billion by 2023. So there is also money in this. This is only AI in imaging. So let's go quickly. What is medical imaging? So the pipeline itself, we start with the scanning the image. So we acquire the data. This is the first step, and we can add AI in each stage of this medical pipeline. Then we can extract the image from the physical signal from the scanner. We get the image. We can enhance it, do some super resolution. Then we can segment some tissues and do some quantification on this. Then we can apply the analysis, and then we can also screen this to the to the clinicals, or having some information displayed for the operators. And finally, what we hope is actually to use this for helping the decision process at the end, which is computer-aided diagnosis. If you can contribute or introduce AI in each step, that would be contributed to the end. And the most valuable thing is the last stage, which is the diagnosis. So what are the challenges in this? Acquiring the data, deep learning requires big data. While in medical imaging, when we scan an image, it takes forever to approve it, and scan one patient, another patient, sometimes it can take a year to build 1,000 subject data set, and also need the approval. There's also, in computer vision, you do crowdsourcing when you annotate the data, when you need some training data, while in medical imaging, we need experts to do this. So it takes time, it's expensive, and also they don't agree on the labels. So you can find two clinicians sitting beside each other, and they give different labels for the same data. Another challenge is different scanner. We also use different scanners. So if you have scan from Philips or Siemens or GE, the data that produce are different. even the sequence can be different. And when you apply machine learning algorithms on these things, of course, they degrade because the data is not from the same domain. And if you go back to the doctors and tell them, can you annotate the new data from this, he will say, like, he doesn't have time. So he will not be so happy by annotating more data just because we changed the scanner. Okay, this is medical imaging like background. I will also quickly explain the machine learning background. So machine learning, you can categorize the methods by training data, like how you supervise when you train data. So if you have this model, like this diagram, we don't have the mouse, it doesn't work. So you train an algorithm based on the medical data, and the amount of supervision, if you don't tell anything to the algorithm and you try to detect patterns, this is called unsupervised. But if you have a guidance and tell this is the output that we need for this task, so you give a data and this is healthy or pathological, and you guide the algorithm to learn what's healthy and pathological, this is supervised. There's something called reinforcement learning. So the previous methods, when you have supervised, you have to specify the task, but you cannot generalize. So you don't get the artificial intelligence that you want at the end. It's still the specific task that you learn. It can generalize to other tasks. So there is a technique of learning called reinforcement learning, when you learn by interaction. Instead of giving label for the output, this is correct and this is wrong, you actually give a signal and let the algorithm learn based on this signal. It's like a positive and negative reward. So if you do this, you get positive reward. If you do something bad, smoke cigarette, you get negative reward. And this is done in sequential steps. So you take an action, and you need to make a decision every step, or every state in this case. So this can generalize to different actions. So you can do several tasks based on the actions you take. And also, it opens you to sequential solution. You don't have to do one thing. It can continue learning. Good. I have to go to this next slide. So this is the only mathematical thing I will show. This is how we optimize the thing. So reinforcement learning was applied mainly or heavily in computer vision for Atari games and robots, but not as much in other applications. So in computer game, because you have the same environment, that there's a player who plays and interact with the environment and try to finish the game and achieve several tasks. So it fits the problem, and they use it as simulator to apply the algorithm there and have benchmark from this. So what happens, you have the, Sonic, the video game, and the agent here, or the player Sonic, try to interact with the environment, gets a frame from the environment, and based on this frame will take an action, go right to collect probably coins or rings, and then take this action, send it to the environment send a new frame to it, and with the reward. And every time the agent displays this game, he tries to maximize this reward. So this is the mathematical model, how we formalize the problem. We have summation of rewards that we want to maximize at the end. If the agent learns to maximize this summation, then he will succeed to solve the task. And this is a loss function that includes target network, and it's DQN proposed from DeepMind, and he tried to apply something called Q-learning, combine it with deep learning. And in Q-learning, you try to optimize the quality of taking an action in specific state. And this is the equation that we try to optimize. We can go through it if we have time afterwards. So why we use RL for the medical application now? So RL, the mathematical also advantage, we get non-differential problem because of the power of the reward. So you can include any reward signal, and you don't have to optimize this signal. It just optimizes the final equation that we showed before. And also it can generalize to different tasks, as we said before. It can learn by demonstration, the same as AlphaGo when there's interaction with players. So you can also interact with the operators, and the algorithms can be smarter and learn. Also, it can learn from unlimited number of samples. So you don't have to generate many labels, because you can generate many states. And these are your samples every time. Okay. So in medical imaging, we have seen artificial or reinforcement learning agents. And the main thing, we want to do this game on medical image. So what will I be showing here is detecting some anatomical landmarks the same way. We have a 3D volume, and the agent sees just a small square and try to find anatomical landmark from unseen subjects. The same, we also try find a plane navigates in a 3D image and try to find a plane that is important clinically. In the literature, there are some people already use this from 2003 or 2006 before deep learning, because reinforce itself is an algorithm for optimization, and then people use it for image localization, landmark detection, image registration, and view planning. And we will show the two examples here. Okay, for the anatomical landmark detection, we define the problem as 3D volume. So in games, you have the environment given to you, while in our medical images, you have to design the environment yourself. And this adds difficulty in the problem itself, because you have to design the reward signals, you have to design the states, you have to design the agent, the whole pipeline. So you have the environment, which is the 3D volume. The agent sees only the 3D cube that you see, the region of interest, and takes an action, try to move up, down, right, left, or upward, or backward. And every time he tried to find the best trajectory toward the target landmark. Starting from anywhere, this agent should reach this landmark. And this is the elements of the pipeline. We have agent, which they interact with the environment, the one we see. So, and the stage, which is like the 3D cubes, small 3D cubes from the 3D volume, and the navigation actions. This is the network architecture, which is simply some conv layers, then fully connected layers, and the final one is your action space. It approximates at the end the quality of taking one of these actions, and it should give you higher quality for the one that goes to the target. It's in the policy. You also need to design a reward signal that is meaningful, which means that if the agent takes a step toward the solution, you should get this positive reward. And the value should be also in a range that can be learnable. So your equation doesn't diverge. It's math at the end, and you need the numbers to be close and consistent with the weights and the reward and the cost and everything. So here the reward, we define it as the relative distance error between the current step and the next step toward the target. So you find the distance between this current step, the point with the target point, and the one from before, and see the difference between them. If they are positive, means that you are going toward the target solution. If it is negative, then the difference, you are going farther. Okay, good. We here do it in ultrasound images. Also, the numbers show that they actually really achieve state of the art. So they improve upon the previous methods. And these are playing in real life on unseen images. This is an ultrasound image, try to find CSP point or the right cerebellum or the left cerebellum center. And using different architectures, DQN-based architectures, and also using fixed scale and multi-scale when you can see only one small, your reception field is small, or when you actually use bigger reception field and you can down like multi-resolution in this case, and jump and move faster. So at the end, the agent find them in a nice way. We also did this with adult brain data, and you can see it also worked nice. The fixed scale is slower because also it used only like fixed scale, one step per, like 1 pixel per step. It moves 1 step every time. While the multi-scale, actually the step is bigger, depends on the scale. So it's faster at the end. We did also with cardiac imaging, finding some anatomical landmarks like the apex and the center of the mitral valve. And you can see it's even difficult for us to find these points. And this is why we have inter-observer and intra-observer error. If you label this point today and you label it tomorrow, you may actually introduce an error as well. Okay, run times, it's very fast. It takes like 0.5 to 1 second to find the landmark from the whole 3D volume. So it is fast. The second application is automatic view planning. So similar to the anatomical landmark, I probably didn't mention the motivation for the anatomical landmark. they are important because they define a quality measure for the images, and also they use it to align the images to the standard coordinates when you can compare between also like population, and you can do the diagnosis at the end. The same with the view planning. When you scan the cardiac, for example, you need some two chamber or third axis or the four chamber view, and based on this ones you can have approximation for the size of the heart. And to find these manually, you will do this procedure, for example, which include like 5-6 steps, defining different views, moving the scanner and the coils, and start finding another view, and then you acquire the scan. And this is slower and needs experts, so every radiologist would be different than the other one. So we can automate this the same way if we train artificial intelligence. We do similar architecture, but in this case, instead of having a point, we have a plane. And this plane is parameterized like a four parameter equations. When you have simply norm of the plane and the origin, 3D origin, the norm have directional angles, and based on, you can move these angles step by step, and also the shift from the origin towards your plane. So it's 4 parameters at the end. And we update these parameters. So similar to the previous method, the agent learns to navigate in the 3D and sample new planes every time, and the new planes goes into the model and do sequentially till it finds the target plane. The reward signal here was the Euclidean distance, the same distance, but in this case in the parameter space, when you use the Euclidean distance between the parameters instead of the points. Experiments, we run similar experiments. So we have, for a chamber view from short axis, you start from anywhere, and this is what the agent sees, like a small square around the center, and try to find the plane on the right. So the one on the right, the plane never saw it. It saw it in the training data, but not in the test subject. And it tries to find this plane, and it goes around the whole 3D volume, just navigating around it, till it finds at the end. And this is like, it repeats itself. We did the same with the axial image for the brain. So we have this, yep. It tried to find an axial ACPC plane. These planes are required clinically, and they can diagnose anomalies based on them. Okay, it finds at the end. So runtime again is very quick. It takes 2-4 days to train and 2 seconds to find the correct plane. So I will conclude the scientific part here, which is the current challenges and future work. So now we are working on something called competitive or collaborative multi-agents. So instead of detecting one plane per time or one landmark, we can train multiple agents that they can communicate with each other and to try to find multiple landmarks, like right eye, left eye at the same time. And they communicate with each other when they train. Also something, it's very interesting to learn from experienced operators, as mentioned before, and have interaction with some of the physician or the radiologist, and teach or fix the errors that the agent produce and learn from it. So in general, you can find that deep learning now has great potential for like applying intelligent computer-aided diagnosis. Hopefully at the end we can reach something there, but you can see it's still far. It's really hard to happen anytime soon. Validation is challenging as well, because you don't have always the right ground truth. Okay, good. The code for it. So I will not dive into the code too much, but it's based on something called TensorPack, if people are familiar with it. Have anyone heard about TensorPack before? Good. So it's like another wrapper around TensorFlow, but it is really efficient. The guy who implemented it is really smart. The main advantage of it, they replicate many examples from state-of-the-art methods. So when they publish code, they achieve the results that you get from the paper. So you can trust the implementation, and it's not one implementation. Plus, it is quick. It relies on multiple GPUs. You can, if you want to extend the speed, you can use multiple GPU as well. The configuration or the modularization of the project is similar to even TensorFlow. It wraps the data loaders. You can use any data loader, the customized one from this TensorPack, or even the normal TF dataset or the TensorFlow record. The training there is this input source that feed or represent the API between the data and the queue to the trainer, and then you use the trainer as infinite loop and you trigger callbacks, and these callbacks are handled by TensorFlow session run hooks, so similar somehow to what we have seen just before. It relies on the hooks, and you can trigger anything that you want during training. It's not difficult to train. The model, you can use any model as well. From the TensorBack models itself, you can implement your own model, or you can use from TensorFlow or Slim or anything. It's compatible with the rest. Good. So this is, I extended this for the application for the reinforcement learning that I'm using. So if you go to our GitHub repo, there's something called TensorBack Medical, and you will have our modules, the DQN implementation, which contains the main file and the main model that you can play with. It's not very difficult. And the data reader, which is the medical data loader, because we have different kind of images, that natural images, so we need to decode the medical images and extract the patches and feed the queue, and doing this in parallel while you're training the model and you're still extracting samples. This is working, so you can even play with it. The medical Python file is the environment. You have two environments there, the landmark environment and the Python environment. This is where the 3D volume implemented, and the sampling and the steps and the actions and the terminal when you terminate, and defining the reward, playing the task or training, and the cost and everything. Experience replay is the memory where you store your samples, and this is where you sample from and train. So you have the memory, which is introduced with the DQN. It was actually before the DQN, but with the DQN, and this is a module for it. The viewer is the one that you see that visualize the agent playing, and this is also can support saving GIF for the agent after playing, or you can save it as video, or you can even display if you want. This is the usage. It's easy. You have the DQN file. You use any GPU. You can define the GPU, load the model if it's trained, the task play or evaluate or train. The algorithm, there are 4 algorithms for now, DQN and double DQN and dual-link double DQN. And the files is actually the training or testing file that you pass to, plus some options for the log directory and the name and other thing. So there are trained model online on the GitHub. You can try it, and there's also test subject that you can play with it. Just if you go there and you can run the command and play with the subjects. Good. So this is for the part we explained. There are more work using TensorFlow for medical imaging. This is a nice toolkit also from Martin and Nick from the same research group, my colleagues, and they did implement many methods that we have in computer vision into medical imaging, and they have model zoo there as well, so you can play around with it. It is very easy to use and simplify the application of medical imaging if you are used to it. And this is it's called Deep Learning Toolkit. There's another one also from Kostas or Konstantinos Kamisas. He designed like the same as he explained before for the 3D unit. There's something called multi-scale. It's called Deep Medic. This is the fancy name for it, but it's like a multi-scale 3D network, or CNN. It's one of the first that tried to implement 3D convolutions efficiently on medical images. And on BRATS, it won the prize for 2017 in the medical imaging conference that we have. So in many applications, actually, it achieves really good results compared to unit or the naive methods. Yep, and this is the topic for it. Yeah, so that's me. Thank you. Yeah. Just like thank the people also from the Bimedia group we have. Yeah. You want to question?
Quick question. So the Deep Medic toolkit, is that open source or?
It is, yeah.
It is open source. So have you built your work based on Deep Medic?
The one I presented, no, but I have this work is mine based on Deep Medic, the one with the placenta.
Okay, so you've got your model based on. Okay.
Not the one I showed or explained now. It's total thing. This is different task, which is like segmentation. It's the one that Bratz, but it was for different tissue, which is the placenta.
So have you kind of benchmarked, like, kind of look at the...
Oh yeah, this paper has like, I think more than 400 citation now. It's benchmarked with any segmentation method people apply. And usually it competes with like 3D unit, for example. Yep.
Is there, so the question was your data set? Like where do you get your imaging data? Is there like the equivalent of ImageNet for medical data?
Not the same size, but we're trying to have this. So the ImageNet is image classification and it's natural images, while the human body has many different organs and different scanning. So there's MRI, ultrasound, and there's heart, cardiac, brain. So some public data set like ADNI, which is for Alzheimer, brain Alzheimer. And we have the UK Biobank, which is huge data that acquires evidence public, but you need just to sign some agreement that you don't de-anonymize the data if you use it. Just don't try to do this. UK Biobank. And they have, I think, MRI and CT scans for the whole body, and start from the brain and the cardiac. And yeah. They're acquiring every day, but labeling the data is still an issue. So it's not benchmark. You have raw data, but no one labeled it. And if you start labeling it as a research group or a company, you don't share it with others because they would publish from your work. So, but there are some benchmarks for challenges on our conferences. Still smaller data sets compared to ImageNet. Yeah.
There's some data sets on Kaggle for this conference as well.
Kaggle?
Kaggle, yeah.
Yes, there are some also data on Kaggle as well. But will be specific for not everything in medical images would be specific task.
Just like to ask what kind of resources for a machine to do, even to display with your examples. Just one GPU?
Yeah, sorry, I didn't mention this. So my experiment will run on GTX 1080. Yeah, that's it.
And how much RAM would the machine need?
Don't have the numbers, but I guess would be
GTX 1080?
GTX 1080 is like 11 gigs.
Like 11 gigs.
Yeah, but I use I think 4 gigs or 6 gigs for this data. You can because changing the batch size is critical for especially for reinforcement learning. It's related to the optimization problem that many negative rewards, and you don't want to like the reward signal does like this for long. You want to cut it and another one. Yeah.
I mean, are there details on the GitHub?
Yeah, it's open source. You can the code is there.
But of the resources we might need to.
The resources, you can use any resources based on your data. So if the data is big, you will need bigger resources. If it's small, 1 GPU will be fine. GTX 1080 is not, it's 500 pounds, something like this, or 600. So it's not something crazy. You can find it in a normal machine. Good. Okay.
Any more questions?
And for the landmark detection problem, did you also like compare it to just a normal object detection CNN? Like,
I compared it with 2 different methods. One of them, not for the view planning, not the landmark. The landmark I compared with random forest and CNN reinforcement learning. Yeah. Okay. And landmark I compared with the reinforcement learning state of the art with a guy who published before me, and this guy he compared with 5-6 CNNs from Siemens. So the thing with Siemens, they have their own data, it's not public, and they have like internships coming and they publish from this, and they just have table for data set. You just apply new method and you add yours in a new row here. So he did this, he achieved better than all their previous method, and they have the state of the art. We can't compete with them, and I achieved better than him. So technically this is also like better than a state of the art. And in the view planning I compared with the CNN because there was no publication, and it worked in the similar way, iterative way as well.
and do you have any intuition on why the reinforcement learning approach works better than the CNN?
So
Like, where's the information coming from?
so whenever you have like label and you're easy to classify, doing classification, there's no complex problem, supervised will work fine. But when you have like landmark, so you have only one landmark here, So how many positive samples in the 3D volume you have? It's only one. And there is probably like 30,000 points that are negative samples. So when you optimize this, it's only one positive sample, the rest are negative. So you have to divide the search, some people divide the search and the localization as two different things. So in landmark detection, when you do the reinforcement learning, this is done automatically because you learn the search while you're trying to find the points. Plus the other things like that we mentioned before for reinforcement learning, the advantage of using it. You have like these positive reward samples, so you always have labels for your samples. When you learn the trajectory, if you move like this, it's positive. If you move like this, negative. So you have always positive and negative sampling. It's like adversarial samples during the training. It generates automatically without your interaction.
How much variation is there between anatomical features between different people?
Anatomical features, like what exact feature?
Some part in the brain. How much do you expect that to differ between
So
A and person B?
cardiac images, for example, are difficult. Brain images are easier, but also not all the brain images. If it is neonate or fetal, it's more difficult. While adults, you go there and you stand like this standard coordinates. You listen to what exactly the clinician told you to do, and you go to during the examination, and done. So it is slightly standardized. While if you scan a fetus, for example, he moves all the time. You cannot stop him, and then you have lots of variation. And the baby can in this orientation, can be in this orientation. The cardiac, the same thing. The cardiac is not all, it has specific orientation that's not flipped, but still it's not exactly the same from each other, and it moves. So it does this all the time. And you have noise around the cardio images. Around the heart there is noise. The stomach, the lungs, they are different from person to another. So
But something in the brain wouldn't be too different between two people unless there's like a pathological issue with
there is high similarity. Like white matter will look similar. The tissues, gray matter will look similar. But if you have disease or pathological cases, you will have different appearance. The tissue will appear differently. But still, this is how they diagnose, because they know that if you have tumor, it will look like, actually we have tumor here, it's good. So you would look like that red circle there. This is, if there is no red circle, you will see it, yeah. Or the white part here, yeah, this one. Do you see this? It looks weird compared to the rest of the image. So they know that it appears differently. And they try to investigate the grades of this based on the pathological cases. The more pathologies they have, they try to compare between them and analyze what are the similarities, and this is like severe, this is not severe, based on how they appear. But like disease specific and organ specific as well. It can be easy or difficult problem based on the organ. Yeah.
Do you have images? How do you detect that there is no issue at all? Is it like in your?
First of all, I'm an engineer. I'm not a clinician, but
Yeah,
but we learned actually this because the problem of annotating the data. This is not in computer vision. We have to somehow, instead of waiting for finding some kind-hearted doctor to annotate or find master student to annotate the data for us, and even if we find them, they annotate it wrongly, not correctly, not all the time, then we have to correct it ourselves. So annotating the data, we learn by time to know exactly what is wrong, and then we send the data to some clinicians, we discuss with them what's wrong here, and they give us feedback, we fix it, and then we do it again. And the benchmark data that are generated, they're generated from some clinicians. So it's approved by some clinicians.